In this video, we're going to talk about Newman projections. We're going to start off by looking at a simple example in ethane, and then we're going to look at the origins of the stability in that ethane molecule, and then we'll look at a more complicated example in butane. So now let's take a look at our example of ethane when we look at Newman projections. So here I've shown two different structures or conformations of ethane. And what we're going to do to draw the Newman projection is we're just going to sight down that carbon-carbon bond. So in this first example, if we were to draw the Newman projection, the circle represents the back carbon, the dot represents the front carbon. On that front carbon we have 3 hydrogens. And on the back carbon, we also have 3 hydrogens. But if we notice in this Newman projection, all of the hydrogens are staggered or equally spaced around our projection. And we're going to call this a staggered conformation. Now the second Newman projection, the second drawing I have, all we've done is we've rotated around that central carbon 60 degrees. So if you notice in the top, the 2 hydrogens that are in the plane of the board are on opposite sides. We can see this in our Newman projection here. But in this case, the 2 that are in the plane of the board are on the same side. So that's going to change the way that our conformation looks. So in this case, the front carbon is going to remain the same. But what we notice about the back carbon is that these hydrogens are all overlapping where the hydrogens are in the front conformation. We call this an eclipse conformation, where these hydrogens are lining up right on top of each other. As you could imagine, the eclipse conformation is going to be higher in energy than the staggered conformations. We'll talk about the origin of that stability in the next slide. But if we try to draw a picture of what this looks like, here I have the energy, and along here we're looking at the rotation around this carbon-carbon bond. We're going to start off at a low energy for the staggered conformations, and we're going to go to a higher energy for those eclipse conformations. And as we rotate around 360 degrees, we're going to continuously change between the staggered and the eclipse conformations. So in the next video, or next part of this video, we're going to look at the origin of the stability. Why do we see a difference between these two, and how can we extend that to more complicated examples? So in this part, we're going to look at the origin of the stability that we see in these Newman projections. And what we're looking at is what's causing this torsional strain. And torsional strain is a strain that's associated with rotating around a carbon-carbon bond. And there are 2 major theories. One of them is going to be the stability of these staggered conformations, and the other one's going to be a destabilization of the eclipse conformations. So I'm going to briefly go over the stability of the staggered conformations first. And I've shown a staggered conformation here, and I'm also looking at a side view of this staggered conformation. And if you remember, we have this carbon-hydrogen bond. If we think about the electrons in this bond, what do those orbitals actually look like? We have an orbital that looks something like this. So we have a pair of electrons that's associated with that. And what this is our sigma CH bond, our sigma CH molecular orbital. But next to this we have another CH bond, but I'm not going to look at the molecular orbital or the bonding molecular orbital. Instead I'm going to look at the anti-bonding molecular orbital. Remember, when we form a molecular orbital, we form the bonding and the anti-bonding molecular orbitals. So the anti-bonding molecular orbital has a lobe that also extends down in this region. And there's some other stuff that's extended up here as well. So this is our sigma star CH. And what happens is this lone pair that's in this molecular orbital can donate into that molecular orbital that's in the anti-bonding. So this sigma CH donating into sigma star CH is a way of helping to spread the electrons around that molecule, and that gives us an inherent stability. So this is a way of explaining the stability of the staggered conformations that we see. Another way, and a more common way of explaining the difference between these two, is the destabilization of the eclipse conformation. So here I've shown a Newman projection of the eclipse conformation where these hydrogens are lining up in all 3 of these areas. And if we look at a side view where the H's are both in the plane, you can imagine that we have a steric interaction, or an interaction between the electron clouds of those two hydrogens. The problem with this explanation in the case of ethane is this electron density is kind of pointing in opposite directions. And some people would have a hard time believing that these hydrogens, given their size, are really going to impact each other. However, as soon as we replace either of these with a larger R group, the steric explanation or this destabilization explanation makes a lot of sense. So what we'll see is this top explanation is a really good explanation if we're only focusing on ethane. This is probably a better explanation of why we favor the staggered conformations in ethane. But as soon as we start to substitute our ethane skeleton, this becomes a much better explanation for larger molecules. So in the next section, let's take a look at a larger molecule. We'll take a look at butane and look at some of the interactions that we see in butane. So in this example, we're going to look at a more complicated molecule than ethane, looking at butane. So we can see the ethane in the center. We have these two methyl groups on the end to give us our butane chain. So what we're going to do is we're going to cite down that central carbon-carbon bond, the C2 to C3 bond. So if we think about what we get initially, looking at this conformation, remember the dot is the front carbon, the circle is the back carbon. We have a methyl group that's here, two hydrogens, a methyl group in the back, and two hydrogens here and here. Now before we talk about this, why don't you pause the video and try to go through and draw as many of these Newman projections as you can. Then we'll discuss them in detail. All right, so let's take a look at some of the different Newman projections. And I'm going to tell you the trick on how to make sure that you can get all of the different Newman projections that we want. What we're going to do is we're going to take either the front carbon or the back carbon. I'm going to choose the front carbon and hold that static, and we're going to rotate the other carbon in a clockwise or counterclockwise direction. So for me, I'm going to take the back carbon, which I'm representing the motion by this methyl group, and I'm going to rotate it 60 degrees. And if we do that rotation, we go from a staggered conformation to an eclipse conformation. So our front carbon is exactly the same, but now when we rotate this, we have a methyl group here, a hydrogen that's here, and a hydrogen that's here. Now I'm going to continue to rotate around to try to get all of the 6 possible Newman projections that we can draw in this particular case. Now what happens is as we rotate all the way around, we eventually get to a point where we're rotating back to our original conformation. Now that we have all of these up here, let's talk about the different types of conformations that we have. The one that we started off with, we had a methyl group that's exactly opposite from the other methyl group, so 180 degrees. We're going to give this a special name. This is an anti-staggered conformation. And this is really going to be the lowest energy conformation that we can get. Then we go through this eclipse conformation, and we have 2 bad eclipsing interactions that we're going to see here. A methyl hydrogen, and a hydrogen-hydrogen. So if we think about how bad those are going to be, we can actually try to measure those. So if we have a hydrogen-hydrogen eclipsing interaction versus a hydrogen-methyl eclipsing interaction, the hydrogen-hydrogen is going to be worth about 1 kcal per mole of destabilization, and that hydrogen-methyl is about 1.4 kcal per mole in destabilization. So we can try to calculate exactly how bad this conformation is going to be. Then as we continue to rotate, we get to another staggered conformation, and we can see we have 2 methyl groups that are in close proximity here. This is what's known as a gauche interaction, and we will call this a gauche staggered conformation. Now that gauche interaction that we see there, where it's a methyl-methyl specifically for the gauche, that's going to be worth about 0.9 kcals per mole. Then as we continue to rotate, we get to the worst conformation that we have. So we have these 2 hydrogen-hydrogen eclipsing interactions, which aren't that bad, But then we have this methyl-methyl interaction. So this is the worst interaction that we're going to see in a Newman projection, where two large groups are trying to occupy that exact same space. So in this case, if we have a methyl-methyl that's eclipsing, that's going to be worth about 2.6 kcals per mole in destabilization. Then as we continue to rotate, we get to another conformation. If you remember, this is our gauche conformation. So we have that steric interaction there. So these two are going to be at the exact same energy level. Then we rotate to another eclipse conformation, which is going to be analogous to that first eclipse conformation that we saw there as well. And then we finally get back to our original conformation. So we can use these numbers that we have here when we look at more complicated examples if we're trying to get an idea of how bad these different conformations are going to be. As we start to substitute more things around the ethane, we get to much more complicated Newman projections. Hopefully you found this information useful as you start to tackle some of the challenging problems that we have to face.